Okay, hey everybody. Hope you're doing well on this Friday. We are in our first real learning day for this unit, where we're going to be talking about searching, and sorting, and recursion. Today we're going to talk about two different types of searching. One's called a linear or sequential search, and another is called a binary search. These are the two main sorting algorithms that you're going to need to know, not only what they are, but how to code one and how to read through one. So I'm going to kind of go through some of that today. As a linear search is probably the way you would have like typically done a search. We've done searching so far. We've looked for something in an array. We've looked for things in strings. And when we've done that, you've pretty much looked item by item down the list, and that's exactly what a linear search is. It's starting at the beginning, and you search down the list, whatever that list is, until you find the thing you want to find. So, for example, here we are. We're going to look for some sort of value. Find array value. So we're going to find some value and giving that as an input. I'm going to start at an I of 0. And I'm going to go until I've reached just below the length, add 1 to I each time. And I'm going to check to see if the value in our array at that particular I location is equal to my value. If it is, I'm going to return back that location. And if not, it's going to return back a value of -1, which you can see up here. Okay, so if it finds it, it's going to return the index. If it doesn't find it, wherever the index was, if it doesn't find it, it's going to return -1 because nothing is ever at an index of -1, right? Indexes start at 0 and they count up in Java. So -1 is kind of a way to let me know that it wasn't found in this list. So that's what a linear search is. We're going to go through an example of it. I don't think you'll really need a lot to be able to figure it out. So if I was searching for a value of 3, what would have happened is we would have, let me come back here and copy this thing first. So let me come in and get this. Apologize. Okay, I just want to kind of leave this leave this algorithm over here so we can look at it. So we have this algorithm here that we're going to use to find stuff. We're starting off with an index of -1. And so right now my index is -1. And when my I is equal to 0, I'm going to come check numRay. And I'm going to say, okay, is numRay at I? Right? I got to do that check to see if it's equal to the value that I want to find. Let's say the value I want to find is 3. That's the value that I've passed this thing. I've gone basically find ray val, and then I've put in 3. So does it equal 3? Well, at 0, it's 34. So that is false. In that case, I don't go inside this if statement. I go up I to I equals 1, and then I'm going to check the next value. Check 18. When I check I of 1, numRay at 1 is 18. That's also false. It's not equal to 3. Then we check I is 2. So it's going to go up to 96. That's also false, right? Then it's going to go I is 3. It's going to check it at 8. That's also false. And then it's going to come into I is equal to 4. Right now, the whole time our index has been -1 because that's what it got set with initially. And when I is 4, we finally get a true, and that resets my index value to 4. Okay. Now, what's interesting about this particular one, as is different from some others, is it would then keep going all the way throughout until I've got to the end. I mean, yeah, index is now 4, but it's going to keep checking. And luckily, it gets false for all the others, and my index is going to remain 4 the rest of the way down. However, if there had been another 3, it would have replaced my index with whatever that value. So this particular one is going to return the index of the last value that matches. Now, I could have, as soon as it equals, I could have set my index to I and hit return index in there, right? Inside of there. And then as soon as it found it, then if I'd done that inside that if statement, right? So that I'd done some curly cues in there to put it inside there, then this would have found the first one that matches. But either way, I want you to know it doesn't find every single one. It only finds one of them and returns that location, either the first or the last. Most of these are typically done to return the first one only, but this one was written to be able to find the last one. Okay, so that's kind of a typical thing. You search one by one by one until you find the item you're looking for, and then you return that value once you find it. A binary search is different. However, because a linear search can be really time consuming. If we had a whole lot of values, it might take us a really long time. And with this particular search, we're gonna check, we're gonna compare the length of the number of items no matter what, even when we find it. Now, even if we'd done it the way I did it, where we returned the first item, it's possible that I might still have to check every single item because the item might not have been in my list, or it might have been the very last item in the list. So we call this an efficiency rating. That means what's the worst case that could happen, and that would be that we'd have to check n times, which is the length of our list. It's not very good. Um, However, we could do this linear search. Instead of doing a linear search, we could do something different. If we could sort our list. So if we take that list and we sort them out into their in order from least to greatest or greatest to least, then I can check a place, probably checking a place in the middle, and I can see if the thing I'm looking for is smaller than or less than the value that I'm trying to find. And so here's what happens. We check in the middle. The first comparison is made against the value in the middle of the list. And if that value matches what we're looking for, we're done. We get out. Found it, found what I was looking for, I'm done. Here it is, here's the index, this thing was at the middle. If it doesn't match, then what we do is we divide the list in half and we check with only one half of the list. Will either check just the stuff that's less than where we are or just the stuff that's greater than where we are. And what's going to depend is whether or not the stuff at that middle location is greater than or less than our value. Okay. If the stuff that was at that location is bigger than the one I'm looking for, then I'm cutting off all the things that are bigger. If it is smaller than the thing I'm looking for, then I'm gonna cut off all the things that are smaller. We're gonna continue this process over and over and over again. And each time we get to take out half the list. And we do this until we find it or we run out of items. I want you to notice this algorithm is um, kind of weird looking. They've set a bottom to equal 0 and the top to equal the last index, the length minus 1. So we have the bottom index is 0 at this case, and the top index will be, if there's 10 items, it would be 9, okay? Because that's how many, that's the top and bottom index. But what we do is we keep running this thing while the bottom index is less than or equal to the top index. And what we do is if we don't find it, we change either the top or bottom index to a different value. And this is the way that we kind of keep moving things. And you'll get to see this kind of in action here in a minute. I'm going to go through the process, so hopefully it'll make sense. Again, if we don't find it, we return a value of -1. Notice that we have these return statements for when we find the things that we can exit out of our method. Okay, so here's an example. We have this list here. We're going to look for the value of 11. So we start off with our bottom being 0, our top being 0, 1, 2, 3, 4, 5, right? And then we're going to calculate the middle. Well, the middle index is take the top and the bottom, add them together, 5, divide by 2. Well, it's doing integer division, so remember it just cuts off the value. So this is going to have me an index of 2. 5 divided by 2 is 2.5. Cut off the decimal, so we end up with 2. So now what we're going to do is we're going to check to see if does stuff, how does stuff middle compare at the middle compare to the value we're trying to search for. How does it compare to 11? And the stuff in the middle is at 2 is 24. I'm looking for 11. So this value is greater than the one I'm trying to find. And since it's greater, since the stuff middle is greater than my value, then I'm going to change my top value to be equal to middle minus 1. That means my top is now 1. Okay, great. Well, now I get to run through this again. I'm going to go check. I'm going to do 0 plus 1 divide by 2. That gives me 0.5. So that middle is 0. I'm now going to check stuff middle at 0. Stuff middle at 0 is 5. 5 is less than my value. So in that case, they weren't equal. They weren't greater than. So I must do this, change my bottom. My bottom is now equal to my middle value plus 1. So my bottom is now 1 and my top is still 1. Now, when I look at that, is my bottom less than or equal to my top? Yes, it is. So I get to keep going through my while loop. My middle then is also 1. And I'm going to check stuff at middle. I get 11. 11 does equal the value that I'm looking for. So now I'm going to return the middle value. So I'll return 1. Okay, so that was a good example. I wanted you to kind of notice after we did that first one, we found out 24 is greater. We got rid of all the items that were greater in the list. After we ran through the second one, we got rid of that value. And then basically all we had left to do is one more check. Let's kind of see this again. Here's a slightly bigger list. So we'll have a bottom. We're going to have a top. We're going to have a middle. We're going to make a comparison. Okay, and then eventually we'll return something. Our bottom is going to start off at 0. Our top is 6. So our middle is 3. When we make our comparison at index 3, we're checking this time for 44. 21 is less than the value I'm looking for. Since it's less than the value I'm looking for, then I change the bottom value to be 1 bigger than the middle. So I'm getting rid of all these things down, and now my bottom is 4, going from 4 to 6. That middle is 5. 4 plus 6 divided by 2. When I check at 5, I get 48. 48 is greater than the value I want. Since it's greater than that, I need to change my top value to be 1 less than the middle. So my top is now 4. My bottom is also 4. So my middle is 4. And so I'm going to check there, and then 44 equals my value. So I'm going to return 4. Notice that both of these times we only had to do 3 searches, right? It only took us 3 searches to get it down to 1 item, right? And we had how many items in this list? 7 items. Interesting. Okay, here's a slightly bigger list. Now I'm up to 8 items. I'm searching for 18, which you'll notice is not even in my list. I'm going to still have a bottom. I'm going to have a top. I'm going to have a middle. I'm going to make a comparison. And then after that, I'm going to possibly return something. My bottom is going to start off at 0. Since there are 8 items in my list, my top is 7. So that means the middle is 3. Remember, do the integer division. So our comparison at 3 is 7. 7 is less than the value I want to find. So therefore, I have to get rid of it and all the things to the left of it. So my new bottom value is going to go all the way up to 1 bigger than the middle, which is 4. My top value is still 7. When I add those two things up, I get 11 divided by 2. I get 5.5, so I'll be checking 5. The value at 5 is 17. 17 is still less than the value. So in that case, my bottom must go all the way up to 6. So now I'm, let's see, I think that's right. Yep, 6. So now my middle is also going to be 6. When I check it, I'm going to find that 19 is greater than my value. So that means my top has to go to one less than the middle. So now my top is 5, but my bottom is 6. Wait a minute. Bottom is not less than or equal to top. I now exit this thing. I go, geez, I've eliminated all the possibilities here. So I'm going to return -1. Okay, I hope this makes a lot of sense to you guys. This is a real quick look at binary and linear searching. Linear searching is great if is a fine thing to do, maybe I should say, if you don't have any other choice, if we cannot get our data to be sorted. But if we have a large amount of data, we're going to really want that data to get sorted. You can see the benefit here. Even when the item was not in the list and I had 8 items, it only took me 4 different things before, like on the 4th loop, right, is when it exited out really 3 times to realize it wasn't there. And then it started to go, hey, my bottom's bigger than my top, therefore I must get out of here. These are really standard algorithms. These are algorithms you need to understand and recognize. I would also know how to code one. Um, uh, Personally, I think they're really, really useful. Um, and I hope that you found this easy to understand. If you have questions, y'all please send me messages. We'll be dealing with these algorithms the rest of the year, and you'll see them show up on the AP exam and on tests for me. So please send me questions, and I will see you all in class on Monday. Bye, guys.